So questions about assignments or anything like that? Immediately pops to mind anything weird, broken, not working? Okay. Remember guys, if you have any outstanding videos, email me a link to them and I will give you credit, at least partially, yeah.
I was just wondering if we're going to be meeting the week of finals.
Yes, so let's talk about finals. No, we're not going to meet the week of finals. Your final project, which I just uploaded to Moodle yesterday, under this week, is going to be due the Saturday before finals start, which I think should be nice because you won't have to worry about it during the midst of all your exams and stuff. Also, your creativity projects will be due then. I think there might be a short 2-minute video that you have to do that week still. I have to go and check, but make sure that you pay attention to Moodle on those dates. But we won't be meeting, so the last time I'll see you guys is the Thursday before finals. Now, did anybody, I don't know if you guys got a chance to look at the final project yet or not. It's pretty straightforward. You're essentially going to go and find a PopSci news article about some object out there that's not in our solar system. I guess it could be about the sun, but not a planet, right? Something that we've talked about in this class. So star, could be a white dwarf, could be a quasar, be anything you want, really, that you find an article on. I want you to investigate the story a little bit deeper using some other reference that you go out and research and find to sort of go into depth a little bit more than perhaps we've gotten into in this course about how that thing came to be. In other words, what is it? What forms the appearance that we give a name to? And then I want you to give an alternative point of view based on treating it not like a gaseous phenomenon, but like a liquid phenomenon, which is why y'all have to be in class because you're not going to find that in your textbook. I've linked you to a number of papers in the final project so that you can go deeper on the liquid model. They're pretty much all by one scientist because he's the only guy who's worked on it since the 1800s. And so that's pretty straightforward, I think. If you guys have questions like, can I do it on this object or that object, feel free to run it by me. One important piece of this puzzle too is that you won't be able to upload a whole presentation, right? So you're going to make a presentation at the end of this project. It's going to be a video that you film. Kind of like what we've been doing all semester, except it's going to be longer. So if you do it by yourself, 10 minutes. If you do it with a partner, 15 minutes. You're going to have to upload it to your own Google Drive and give me permissions to view the file. If you don't do that, I won't be able to grade it, and your grade won't be submitted on time, basically is what it comes down to. Everybody did a good job last semester with this new method. This is the first year it's been a problem because we lost our uploading platform this last year. Microsoft discontinued what we used to use for videos. So basically what I think the best way to do this is to, you guys all get Zoom as part of being students here. You'll have, you can just do a Zoom presentation and record it. So you can record yourself talking through Zoom. If you want to use slides, and I recommend you do probably show some figures, not a lot, but you need to probably show what you're talking about. You can do it inside of Zoom. You can record the presentation. If you're doing this with a partner, you can both be inside the Zoom meeting, right? And yeah, I think that pretty much covers it. If you're doing it with a partner, make sure you put both your names on it, or otherwise you'll have to submit it twice. But it might get lost in the weeds if you don't put both your names on it. Let's put it that way. What do you think? Questions about that? So don't not do the final project. That will be a surefire way to probably not pass this class. But remember, all these pieces of the puzzle in this class are worth the same amount as far as points go. So, in final projects, worth 15 points. I'm pretty sure attendance is also worth 15 points. Same with your quizzes and assignments you're doing. Everything's worth kind of the same amount. So make sure you get it all in. Look, if you haven't done any of the assignments, you haven't done any of the quizzes, do them by that Saturday. Make sure to send me emails if you're submitting late videos. I won't know about them otherwise. And there's, again, there's no reason for everybody not to get an A in this class. At least an A-. Even if you do terribly on the quizzes, you should be able to get full points on everything else. Just by doing the work. That's all you got to do. All right. Cool. Questions about that? Anybody? Okay. Feel free to email me or come talk to me if you start into it. You don't have an assignment this week otherwise. I think it's just getting, you do have a quiz, but you don't have to make another video. So just start thinking about your final project. Like I said, you're welcome to work with a partner if you want to. But yeah, it's pretty straightforward. All right. What else? So I definitely want to hear from you guys. I've made it through the last round of attendance calls, but if anybody wants to volunteer to remind us where we're at, I'm going to, this is kind of the, let's see, this is the last point in the journey as far as the lives and deaths of stars are concerned, because we have reached the black hole finally. And so today we will be talking about black holes. Now, I'm going to assume you guys have already read the textbook. We're basically one lecture behind, so this is technically from last week's reading assignments and stuff like that. So I am going to put down some alternative perspectives about black holes and try to compare them as best as I can to what's going on here. But does anybody want to just remind us where we got to in the discussion of stars dying, neutron stars, general relativity, questions, comments? General relativity is very difficult to comprehend for most people when they first encounter it. So let's talk about it. Ask some questions. And yeah, yes.
So we talked a bit about supernovas and how.
It's Alex, right, by the way? Yeah. Yes.
And we talked about like how bright they are. And it's speculated that a supernova happens in our galaxy every like 2 centuries. How come we've like never seen one?
I know. Pretty great. Well, we saw one in Galileo's time, but that's down through the chain of communication, right? So we don't obviously have any pictures from Galileo's time. It's pretty interesting. I mean, there's a statistical argument to be given about that, I suppose, that these things operate on extraordinarily long time scales. Where did you get the 2 centuries from?
I think I saw it in one of the articles.
Okay. Yeah, I mean, you know, again, you know, if you, under the standard model of the gaseous sun, pretty much all stars have to go through this final phase where they either give off all of their outer layers in a kind of violent outburst called a nova, or if they're these massive stars that collapse, they undergo this supernova thing, right? In any case, you would think we would see a bunch of these. And so an argument can be given that perhaps we're just not comprehending the geological timescales necessary, and that it's, you know, maybe there's some randomness and stochasticism to this, and it happens with some frequency, and that, you know, hundreds of years is nothing on geological timescales, and so maybe we're just not looking at the time domain properly. On the other hand, with a liquid model of the stars, these kind of violent, destructive situations would be more anomalous. They'd be more akin to exceptions than the rule. So most stars under the liquid model would just cool off slowly. They would kind of roll down the main sequence and fade into oblivion. They would just become dark, non-luminous bodies, kind of like Jupiter's eventually. Eventually they would lose all their outer liquid and atmosphere, and they would just turn into rocky balls, basically. And so you kind of have, just like with everything in this course, you got choose your own adventure explanations for either outcome. So yeah, it is kind of strange and interesting. It's also really, I think it's even more interesting when you couple it to the work of the Vasco project, which is this vanishing astrophysical, I can't remember what it stands for, but basically these vanishing stars that have been seen, right? So there's all these little star-like objects that were seen to just completely disappear over the course of this 30-year time frame. And for me, it's like, all right, that at least at the bare minimum points to the possibility that stars go out in ways that are a lot less dramatic than the standard model would have us believe. So kind of interesting. I do think it's kind of strange. You would kind of expect, I think, given how many stars there are. Does anybody know how many stars there are in the Milky Way? I think it's on the order of trillions for sure, which is 1,000 billion. So it's into the realm of incomprehensible numbers. But you would expect with all those stars that you would see quite a few of them popping off now and then, right? Another corollary to that that's kind of interesting to me is that if you look at that HR diagram that we keep throwing up over and over again, most of the stars are on the main sequence. The ones that end up in the white dwarf space or in the red giant space are vastly outnumbered by the stars on the main sequence. And if you really thought that if you really want to make the argument that all stars are going through the giant and dwarf phase in the course of their lifetime, from where I'm sitting, it seems like they should be at least somewhat evenly distributed across each one of those moments, including the main sequence itself. So that's kind of interesting. Again, you guys know how I feel. I think we're sitting on the edge of a really interesting paradigm shift and all this stuff that's going to really rewrite how we see all this stuff going forward. But not everybody is on that page. Yes, Jasmine.
Stars might have like a less dramatic way. Do you mean like just like, oh yeah, the supernova way? Or because I know that there's where it collapses on itself, it's quiet dead. And the other is
Even in that case, it has to lose a bunch of layers. Yeah, all of these collapse moments generally lead to the casting off of these layers, right? It might be just a regular nova, it might be a supernova. It might be just casting off layers in these planetary nebula, what they call planetary nebula, nothing to do with planets. Those are all like what I'm calling dramatic deaths, right? So the standard gaseous model of these objects always involves some sort of dramatic end to these stars. The liquid model almost always involves a mundane cooling of the body. So the star just cools. It's basically losing mass because all of our star is, no matter how you look at it, the stars are all just spraying hydrogen off into interstellar space. So they're cooling because they're losing all this mass. So under the liquid model, the stars just kind of move to the right down the main sequence. They cool off, they become dimmer, and then eventually they just basically look like Jupiter, or look like brown dwarfs, and then they'll look like Jupiters, and then they'll just continue to evolve. And a lot of how far that process would go depends on the timeline that you're granted for the universe, which is kind of what we're going to turn our attention to next in this course in terms of the story of our universe, which is how much time do we have to have produced the things that we see? How old is this place? That's the big question on everybody's mind right now in cosmology. And historically, it keeps getting longer and longer, so that's an interesting piece of the puzzle. If you have a really long time, well, then you have plenty of time for stars to have cooled to the point that perhaps they've generated a lot of these rogue planets, or they've generated a lot of these rocky things that we can't even see because they're too cold to be picked up by even infrared telescopes. So that's what I'm calling the mundane path, the sort of boring cooling down and losing your light process. Yeah, it's a good question though, good to clarify. What else, guys? Yeah, right.
I thought the talk about metastability was really interesting, that matter transform serves, especially in regards to things like diamonds that seem so indestructible and then they're just change form.
Yeah, that's really crazy. I learned that one recently, which was fantastic to fit into this story because I keep bringing up diamonds and soot as two examples of a pure material of carbon that have very different appearances optically, right? But yeah, it turns out that diamond is a metastable substance. I just learned that last week. Glass is also. So technically, glass is a flowing. It's technically this kind of amorphous solid that's somewhere between liquid and solid. And there's evidence that over centuries, glass can actually flow under gravity and will actually kind of thicken at its base in window panes and stuff like that, which is cool. So there's all these metastable, basically, the phase diagrams that we've talked about, liquid, solid, gas, it's not quite as clear-cut that if you have this exact temperature and pressure, you end up necessarily with this phase. Water can, under certain conditions, if it's pure, there's nothing for the ice crystals to nucleate, you can get water down to like -40 before it'll flash freeze into ice. So that's pretty crazy because everybody knows the freezing point of water is 0 degrees Celsius, right? So yeah, there's a lot of nuance to understanding how these atoms will behave in materials. That's a good point. What else? And that's important, by the way. That's really important for the liquid model of the sun because the pressure at the surface of the sun is about the pressure of water on Earth. The density. The density is about the same as water. The pressure is not adequate to produce liquid metallic hydrogen at the surface, but the theory would hold that it's produced a little bit below the surface. And these things where we see these convection bubbles, if you look at the surface of the sun, I had a picture up here. You see all of these little kind of bubbling structures, right? These convections. And of course, you have the sunspots where you can peer into it a little bit deeper. And the argument is that liquid metallic hydrogen is metastable in so much as it's able to form at deeper layers. Not necessarily that deep, but somewhat deeper and able to persist to the surface to some point, at which point it sublimates, just like dry ice, and turns into the corona and the atmosphere and is given off as solar wind eventually. So yeah, metastability is a huge piece of the puzzle. Now, there's been a couple of papers about the metastability of liquid metallic hydrogen. It is very, very difficult to study these things on Earth because of the pressures that you need to generate it. As you can imagine, coming up with the pressure like you would get inside the sun in a laboratory is very, very difficult. The only way you can do it is really shock loading a system, an experimental setup, so you can measure it for a transient amount of time, but it's very difficult to study because you can only apply that kind of pressure, usually with a laser or some sort of really tightly confined system that's really stiff. So it's very, very difficult, and there's been papers about it, but it's certainly something people argue about in terms of what exactly are the pressures required for liquid metallic hydrogen to form and things like that. And its metastability is also heavily debated in terms of how long it would persist and things like this. So there's a lot of ragged loose ends here in terms of the liquid metallic model of the sun that need to be cleaned up, I think, before, particularly from the experimental standpoint, before people would be willing to, by and large, apply it to the stars. And I think that's a huge piece of the puzzle. What else, folks? Yeah.
Experiments like Edward
Dowdy, yeah. Yeah.
but I don't remember.
Dowdy's like the only mainstream scientist that I know of who's really published on this phenomenon. He was he was a laser optics scientist at the NASA JPL, and he was very skeptical of the interpretation that light could be bent by gravity. And he had a different explanation of the primary data, and he had a couple of really serious criticisms of the idea. The main criticism I think that he evidenced is that, if light is bent, so there's this very famous study, we talked about it, that Arthur Eddington, he really put it together to prove Einstein's theory. A consequence of Einstein's relativity, in particular general relativity, is that light is bent by gravity. So he set out to prove this, and one of the ways he proved it was they knew the position of certain stars in the sky. People have been measuring them for eons. And they said, well, during an eclipse, we'll have the opportunity to see stars during the daytime, stars that are right next to the sun, basically. And so the light from that star should be moved, it should be lensed due to the gravity of the sun, essentially. And so they measured this, and they found it to be the case. But what's really interesting is that according to those same laws, not only should the light that's right next to the sun be lensed, but the lensing should actually fall off with a Gaussian distribution, a very nice smooth curve, essentially, where the most lensing happens right in the center of the body, which you can't see, and it sort of falls off with a very predictable relationship after that. And it's weird because you don't actually see lensing of stars in the solar system beyond, a single solar radii. Basically, it only extends out as far as the corona is visible. And so Dowdy, I think, was thinking this was more of some sort of a lensing process, something like what you would see. You guys ever driven on a hot day in the desert and you see these little mirage things happening, basically? Those are entirely based on density differences due to heat at the surface, right? So the air being the medium that is lensing the light, right? The medium through which the light must be relayed from atom to atom. It's at different densities. And of course, the density, the amount of material there, affects the speed of the light and slows it down due to these relay processes. And you get this weird effect where the road seems to be hovering above the road or something like that. And I think this is kind of what Dowdy was pointing to that may be at play. And he had some other arguments too, but I think that was his principal argument, which is really interesting, which is actually really important as we start to talk about black holes, because the entire argument based on black holes is that when a body has enough mass, it's big enough, that it will essentially lens the light gravitationally so much that it can't even escape from the body itself. So this curvature of lensing will be so intense that it's essentially circling back on itself. Of course, if gravity cannot actually bend light at all, then that argument sort of falls out the window. So that's interesting by itself. What else? Thoughts? All right. Yeah, Kevin.
Going back into the supernova thing.
Sure.
I found an article this week for the video, and it was just pretty much explaining that supernovas trying to, this one specifically, it went through a different process when it was dimming out. It's like the way the inside burned up, it kind of just went by sections.
Interesting.
Yeah.
Like pulsed.
Exactly. It was from the way it was rotating.
Interesting.
The rotation sped up when it was coming towards the end of it, and it was only you could see in the rotation the blotched out of the fire, brighter than the rest of
I saw your video. Yeah, I meant to follow up on that, but I didn't get a chance to.
I'm just in the same area right now.
We'll come back around to supernovas because that's really interesting, and I'll tell you why. So we'll come back to them because we need to start thinking about distances that are unbelievably far. We're going to look at galaxies later this week, and then we're going to eventually start looking at other galaxies and moving outside. The distances, when we're trying to imagine how far away something is, we can't use the parallax stuff anymore. We can't even use the Cephids anymore because it's just too far away. But we can use supernova because they're really, really bright. And so the hope is that there's essentially a constrained number of types of supernova that happen. Basically 2 of them.
But it wasn't either one.
Exactly. So things get really gnarly if it turns out that there's lots of different ways that these supernova can proceed. And this has happened before, it's worth mentioning too, with the Cephids. So when they originally studied the Cephids, they have this really nice pulsation curve to them. And they thought that everything that they saw with the pulsation curve was a Cephid, essentially. And they started studying some different aspects of the fingerprints in the spectrum of these stars, and they realized, oh my goodness, we can actually bend them into 2, and it actually changes the distances that we had by a factor of 2. So the galaxy itself got 2 times bigger overnight, basically, right? And this is kind of a trend that you see happening. I want to be really careful not to sound like I'm sort of in any way condescending on these people who've done all this incredible work. This is just par for the course. I think we have to I really want you guys to come away from this class and understand that this is how science works. There's never a done deal. There's no such thing as settled science. That is a crazy, crazy idea. The fact of the matter is we always can learn new things, and sometimes when we learn new stuff, it totally rewrites everything. Most of the time not. Most of the time it's just sort of, we'll adjust this, adjust that. And we do that until things catastrophically break sometimes. And so, sometimes if you look back over the course of the last 100 years, the age of the universe has gone from 1 billion years to 3 billion years, to 6 billion years. Now it's pegged at 13.8 billion years. You know, there's a trend to this, right? That sometimes it seems like there's a trend to the more information we get, the bigger and more complex everything seems to be. So that's really interesting. I'll try to check out that article before we get back around to it. Heck yeah. All right. Anybody else? Yeah.
I don't know if we talked about it specifically, but on that same note, have you seen like the picture? It looks like a bunch of like weird TV static of the supposed new end of the universe.
Oh no.
It's really odd looking. It looks like a bunch of green and red and black pixels, but they say like that is the furthest shot their telescopes can get to the end of the universe.
Interesting. Are you sure this wasn't the cosmic microwave backgrounds?
I don't know if I'm.
We'll get around to that soon too. Maybe if you see it, if it seems like this, then we'll talk about it. But if you come across it again, send me an email because I'd like to check it out. But it might be the CMB, which we'll deal with imminently. That's coming up.
It looked really weird. It was like just like a bunch of pixels. It didn't even look like it.
See if you can find a picture of it, and yeah, Summer.
Something I keep coming back to as we've gone through this course is Jupiter. And you've talked about how Jupiter is kind of this rarity, and it's slightly smaller than a brown dwarf, right? And it has a liquid metallic hydrogen core. And then we also are in this system that's missing our binary star. And is there any chance that Jupiter ever had anything to do with that, or is it too close? Could it have been a star? Could it be becoming a star?
Yeah. I mean, I think that you're thinking in the right direction for sure. I mean, I think that a lot of I think it's shocking how difficult it is for most people. It's difficult for most scientists. How do I put this? If you're a scientist and you're trying to propose an explanation for anything about Jupiter, the tradition would have it that your explanation be based on the idea that Jupiter formed in the solar system at the same time that the sun formed, more or less, slightly after, but on the same time scale as Earth, Mars, everybody else, right? That's been the paradigm for 300 plus years. You know, nobody in their right mind who's trying to keep their grant alive would really propose anything else. However, the last 10, 20 years, seeing rogue Jupiters circling each other, this is seeing other solar systems for the first time. It's hard to really understand how new that stuff is, and that the students who are coming in and are going to become the researchers and professors tomorrow are growing up with that being the new paradigm, that of course Jupiters can form perhaps without solar systems. Of course brown dwarfs are expected to be very similar to stars, and maybe they spend some time on either side of the barrier, right? So, and of course our solar system is weird and diverse and seems like a little bit of a hodgepodge of different types of planets in different stages of their evolution, right? You know, I think that something brand new came out literally just this semester, which was somebody saw a super Venus. They'd never seen a huge carbon dioxide atmosphere planet. It was basically like a really huge atmosphere version of Venus, right? So now that's of course going to get people thinking, wow, well, what if what if Venus used to look like that, and it just sort of evolved because it was too close to the star at some point. There's just so many constraints on why people wouldn't have written those ideas up in an academic setting. It's just a strange mixture of science being in an academic space where your career is to secure grants, that you need to basically write safe stories based on the entire wealth of what came before you, married to how new all this data is, which is just extraordinarily new in terms of if you think about the 300-400 years we've been studying all this stuff. So, yeah, I think you're thinking along the right direction. What did you guys find out?
It was an X-ray X-ray thermal.
of it.
Telescope.
So I was half right.
Okay.
I was like, it is at the end of the universe, sort of, but it's the X-ray image of it. You can't actually get like an image.
That's how we get the
image
telescopes to look that
of it.
far, into that many light years away.
Yeah.
So they're X-ray.
You need that high energy light, yeah.
Exactly. So she was saying like it's a green, red, yellow. I'm like it's just heat
It
signatures
is.
of how far it's looking.
I see. We'll deal with the edge of the universe soon enough. We'll get there. We're not quite ready for that yet, but we'll don't worry, we'll get to that stuff. But I think Summer brings up a really good point, which is like Jupiter is an interesting Rosetta Stone in some sense. I think brown dwarfs are equally interesting. We just don't have one that close to us to study. But Jupiter is fascinating because it is essentially similar in composition to the star, our sun. It even has some interesting pieces of the puzzle, including the liquid metallic hydrogen core, which is also a brand new idea as far as I can tell. That was not in the textbooks when I was a kid. And now, by the way, if you look in the I don't know, I haven't checked your textbook on Jupiter lately, but it's expanded outside the core now. So they thought that the liquid metallic hydrogen exists at a much greater depth, a much shallower depth than the core itself. So these things are just always on the move. I think that's kind of the fun part about astronomy as non-scientists, is because it's like one of the scientists, it's the science I think that's moving the fastest, it's changing the fastest. A lot of other stuff, chemistry, I don't know, it's not moving as quickly. People aren't really radically altering the way they think about it. But yeah, there's something really, really unique and interesting about astronomy. Perhaps because the conclusions we draw can only come from light, right? So we're bound to misinterpret something as subjective as looking at light and trying to make sense of it. It's bound to happen, I think. All other sciences, we can at least put things in test tubes and run controlled experiments, Can't do that with stars. So
Be cool.
it would be cool if we could. It would be cool, yeah.
So if it turned out that the sun did have a liquid metallic hydrogen core, then it seems like Jupiter would become the new Antarctica, like you would want to get as close to it as possible to study as much about it as possible, right? If they had that connection between them, is it feasible in the next couple hundred years for humanity to actually study Jupiter that closely, get some sort of outpost over there? Or is that just totally?
Yeah, I think it's all underway. There's a lot of missions going on to Jupiter right now. I think it takes 5 years to get there, which is a little obnoxious. But yeah, I think there's a European mission. There's a NASA mission going out there. A lot of the problem with studying Jupiter is going to be setting up some sort of outposts, not for humans probably, but for robots. So they're probably going to put up some sort of base on one of the moons eventually. And by base, I probably mean just some collection of antenna and stuff. Now look, the pressure, I don't know about firsthand studying the interior of Jupiter. That's kind of a little bit beyond my imagination in this technological kind of ecosystem we're in right now, because the pressures are extraordinary that would be required to get down there. I think any spacecraft we could build would just get destroyed. So I think in terms of understanding liquid metallic hydrogen, a lot of the processes focus on just shock loading hydrogen for just an instant and trying to study things like the electrical signals that change, how it becomes more metallic, really trying to study its metastability, how long does it last after you shock load it, stuff like that. I think in some sense, the more you understand about the phase diagram of hydrogen, liquid metallic hydrogen, the more understandable it becomes that people haven't been able to consider it as a possible state for the sun, because it's just been so difficult to study here on Earth as well. So, and then especially in terms of the lattice structure, what is it? That's also deeply theoretical at this point. It's as long as you can't stably produce it in a laboratory, it's going to be very difficult. I think we'll be able to eventually, but there's only a few groups, to my knowledge, working on it. There might be a lot of secret groups working on it, state secrets, but there's only a couple above board that I can see. So, kind of interesting stuff. Hopefully you guys will go a little bit deeper. You can read about liquid metallic hydrogen for your final projects and whatever you're studying, and kind of compare it against it. But compare whatever object you pick against the gaseous model versus the liquid model. I think that'll be really exciting to see. Cool. All right. Anything else? All right. All right. Well, let's talk about black holes then. Let's give black holes their due. Make sure I followed everything here that I wanted to get to. Okay. So nobody mentioned anything about general relativity from our discussion last week. I don't fault you for that because it's a strange piece of mathematics, and this not being a mathematics course, I'm not sure even to what extent you're able to formulate questions about general relativity. But the basic idea is, of course, that, motions, let's say, do appear to be in some sense relative. In other words, if you ran by this desk right now, it would be a reasonable case for you to make that the rest of the room was moving and you were the one standing still, at least if we looked out of your eyeballs. And this is actually kind of goes back to the way that people first understood the solar system, right? For thousands of years, until Galileo, essentially, we had this idea that all of the stars are moving around the Earth, right, above our head every night. And it's absolutely true. They are doing that. Like, when you look up, the stars do move by, right? And this is kind of the basis of relativity. It's like, look, we have to actually consider all these perspectives when we look at a physical phenomenon, because it is true that from my perspective on Earth, the stars are moving overhead. But what's it look like from the star's perspective? Well, it looks like the Earth's moving. And it turns out that that's a perhaps more productive lens to look at the situation from when it came to setting up the heliocentric model of the universe. But relativity does that sort of integration of perspectives in mass, right? Now, the annoying thing is that, first of all, it's unbelievably precise. It does seem to improve upon Newton's simplistic gravitational equation. So it's really good at what it does. It does give us very good descriptions of how bodies move with respect to each other. The trouble with that is that descriptions are not the same as explanations, right? And so many people, and I think even the way that your textbook probably describes this, although I don't have the quote in front of me, would be that it's the best explanation that we have for gravity today. This is tragic because it is actually not an explanation for gravity whatsoever. It's in fact just a mathematical description of how gravity seems to play out in the universe when you parameterize the world into masses and distances between them, and move it into the dynamic domain where you add time in as well. And so a bit of the tragedy is that if you think that describing what's happening on the stage of, say, Peter Pan is sufficient to explain how Peter Pan is flying onto the stage, you're going to be woefully misled, because you might not have noticed that Peter Pan was attached to the ceiling with strings, because that wasn't available to your perspective. So I think that this is going to be a story today about something called boundary conditions, which we'll get into. And it's going to be about the human need for magic, really, too, which is really interesting. And I'm going to try to weave those together into something that makes sense. I also want to talk about this, because this image made big did anybody see this in the news when it came out? Yeah, a little bit? Okay, well, so this was supposed to be the first image of a black hole taken ever, basically. Now, this image did not appear in your textbook, and I think I know why. So I'm going to walk you guys through exactly what's going on here in this picture. But I think at the end of the day, we're going to try to understand, not only the gaseous model of the black hole creation, but also like some more mundane alternatives, and also why it's such an appealing model, right? Because black holes are incredible, and they're at the center of a great deal of wonderful science fiction that I'm a huge fan of. And I think that there are some metaphysical reasons for why we want them so badly in our universe. So let's talk about this a little bit. Like I got into last time, and we just talked about this, so I'm not going to linger on it too long, but we talked about the idea of space being curved under general relativity as a result of gravitational processes. In other words, these big massive bodies actually bend light itself. So the downstream consequences of that being that if your body is big enough, that you're going to actually bend the light right back onto yourself. Now, there's some interesting corollaries of this, and of course, I expressed some skepticism of this through Edward Dowdy last time, but there's some other really interesting corollaries of this. So another one that's quite intriguing is this thing which is called, doesn't really matter the name of the experiment, it's called Shapiro time delay. So they basically send these signals between, Viking was a mission, I believe it was a Mars mission back in the 70s. Anyways, they're communicating with this satellite, for lack of a better word, this spaceship, as it's on the other side of the sun. And what they notice is really interesting is that when it's, let's say, off to the side of the sun, so we have a direct line of sight with it, that the signal appears to take a certain amount of time. And then when it goes kind of towards the back of the sun, so the sun is in between us and the satellite, that it actually seems to take longer for that signal to get there, which is really intriguing. And of course, people jumped on this to justify that time itself slows down in the presence of these black holes. Now, again, I think that Edward Dowdy's work also can shine some light on what's going on here too, because of course, when you have a medium, light travels slower in medium, right? So light travels slower inside of water than inside of air, for instance, and much slower than inside of a vacuum. Now, there's every reason to believe that near a body like the star, like one of these luminous bodies like our sun, that it has an atmosphere that's actually quite dense at its surface as it's sublimating off the surface. And so there's a lot of relay events necessary to move that radio signal, that light signal, from the spaceship through that atmosphere over to us. And we see this in our own atmosphere. It's the reason why light turns red at sunset, right? You have more atmosphere to shine that light through of the sun when the sun is low than when it's directly overhead. You just have a thin layer. You have this whole layer of atmosphere when you're looking at it at sunset. It reddens it, right? Not because time is slowing down, but because there's more relay going on inside of that system. So I'm not entirely sold on this being a matter of time itself. We also talked about the different clock systems, right, and what time means in physics. Does anybody remember how we defined what time is in physics last time? Yeah.
It's the thing clocks do.
Yeah, it's just what clocks do, right? And so we can come up with really precise clocks. In fact, the most precise clocks we know of today are these atomic clocks that are based on how much the atom essentially vibrates per second. But why shouldn't clocks be affected by gravity? Like every single other clock that I can think of is affected by gravity, essentially putting a great deal of strain and tension onto a mechanical system, even if it's just made out of one atom. Of course, these aren't made out of one atom. They're made out of crystals of lots of atoms. But why shouldn't they be, in some sense, strained under the pressure of gravity? This makes a lot of sense to me. No need to actually warp the idea of time itself. So, okay. So that's the time delay situation, light bending. People, it's really quite interesting, the history of this idea of black holes, because the idea that perhaps, something could be massive enough to actually bend all this light away is really old. It goes back to the 1700s. It was developed over the next couple centuries, and then really Einstein's general relativity provided a situation where somebody could actually solve for what radius would be required where that light, radius and mass would be required where that light would not be able to escape anymore. We talked a little bit about this before with this diagram over here, which when we were talking about white dwarfs, like exactly how much do you squish these things down? Now, what's really crazy about this is that these are solar masses, right? So anything that's really not that much bigger than our sun eventually, once under the gaseous model, it exhausts its core fuel supplies, is going to start to head down this trajectory where all of that mass is going to start squishing it because it doesn't have that radiation pressure in the core. All that gas pressure in the core is going to die out. And so it's going to start crunching on itself under this model. And so, of course, what's really interesting is that the radius of the star starts dropping. And for stars that are, a little bit bigger than us, at some point it's going to reach this zero radius moment, which is really, really fantastical. And this is called the Chandrasekhar limit. So Chandrasekhar was the guy who took that solution to Einstein's equation, which is called the Schwarzschild solution to Einstein's equation, and he applied it to the stars. And he said, I don't think what Schwarzschild did with Einstein's equations is just a mathematical anomaly. Of course, Schwarzschild, when he published it, he thought it was just a fun little game. He said, hey, look, Einstein, I think that if we have too much mass in one place, that your equations are going to tell us that there is essentially the creation of this infinitesimal point where everything is going to collapse upon itself completely. But he thought it was actually, I think Schwarzschild wrote this paper when he pointed out this mathematical artifact of Einstein's equations. I think what he was trying to actually say was, hey, Einstein, I think this is actually the boundary upon which your theory stops working. In other words, I think that this model of relativity works up to a point. It works up to the point that you have this much mass in one place. So there's two ways to interpret that. One is that that's the physical limit of the compression under this model. And the other is that beyond this point, physics breaks down and unbelievable supernatural phenomena happens, and you end up with ultra-dense things and stuff occupying no volume and things that are kind of unimaginable. So in Schwarzschild's day, when he actually did this calculation, I would hazard to guess that he was actually trying to put a constraint on the theory, on Einstein's theory of general relativity. Now, this is a really common thing to do in science, by the way. So this is where we need to talk about boundary conditions. So, have any of you guys taken like a science lab before in high school or anything like that? Where did you have to take some data points at some points and then fit like a line to them or something like that? You guys have to do this before, right? Pretty standard, like intro science stuff. So, that's a really generalizable thing that we do in science. Take all these data, and then we try to put not necessarily a line, but some sort of curve that we fit to the data, right? It might be, if it's a line, we get a really nice equation like y equals mx plus b. You guys learned this in 8th grade or something. If it's a curve, maybe the curve fits to like y equals x squared or something like that. Maybe it's a different curve, it's like e to the x, right? So you get these kind of exponentials and these polynomial versions of these curves. In either case, you're basically trying to find some line, either a curve or a straight line that fits the data, right? Now, we do this all the time in science. But the thing that we do in every other science that they didn't do with the black hole situation is that we always constrain the x-axis to where we think it actually applies to the reality of the situation. So when we're modeling something, some actual phenomena in the real world, it could be, let's say, I'm trying to think of something that would fit to a line really nicely. Perhaps just you're just measuring velocity, so distance versus time. You run a clock and you measure how fast somebody or how far somebody moves at each point, and you fit a line to it, you get the velocity of that person's motion, right? Well, you wouldn't extend that line back down below the 0 points of the axis, right? You wouldn't imagine that the person goes backwards in time and has a negative time at any place just because you measured that their speed is forward in the first place. You would constrain that situation to physical reality. And every single science does this all the time. So what you do is you say that our theory, our curve fit, our mathematical model, is applicable to the phenomenon we're studying where x equals this to x equals that. Let's say between 0 and 100, or 0 and infinity for the case of the velocities, right? Otherwise, you have to start either bending physics or thinking about new interpretations of what's going on. Now, there might be a rational interpretation for moving backwards into the non-physical side of that equation. Like you might say, okay, well, the person's just walking in reverse, or they started before the timer went off, or something like that. There may be justifications for extending those boundary conditions down below the 0 point on the axis. But in general, you have to consider what's a realistic portion of this curve to fit to it. You can't just use the line because the line fit your data. You don't get to just extend it indefinitely without justifying the physical conditions of that. So what's really weird and unique in all of science, from what I can tell, is that this is one of the only cases where instead of actually constraining the boundary conditions, perhaps like what Schwarzschild actually intended to comment on in his original paper in the 20s, instead of doing that, people, including Chandrasekhar, decided to imagine that physics itself broke down, that reality itself broke down, that somehow all of this material could be squozen into a point that had absolutely no dimensionality to it, a singularity, a point of infinite density and zero volume, right? Now that's a really interesting and arbitrary decision to make, but it does seem to have caught on. And it does seem to have enabled the production of explanations for this phenomena that we do in fact observe. So, one of the things that's worth pointing out is that these objects that we're talking about today, these black holes, there does seem to be something weird happening in a number of places in the universe, including at the center of our own galaxy. There's places where objects appear to be rotating something that we can't see, right? And so, if you process the ideal gas laws as Schwarzschild did, as relativity does, as Chandrasekhar did, following the Schwarzschild solution to Einstein's general relativity, you actually do end up with a situation where you can explain how something can be supermassive but invisible, right? So it is an explanation for what's going on. The question is whether it's the best explanation for what's going on. Are there other reasons that things might appear to be orbiting points where we can't see any light coming out of those points? And I think we already investigated some different ideas for what that could be. It's worth pointing out, by the way, that this has happened before in history. Have you guys, anybody ever come across this idea called the ultraviolet catastrophe? Probably not. Anybody? No. So, the original, way back in the day when people are first studying all of these heated bodies, these black bodies and so forth, the classical equations that they used to fit the slope on these black bodies predicted that as you got into smaller and smaller wavelengths, like as you got into the ultraviolet and into the X-rays and the gamma rays, really, really high energy light, that essentially the intensity of that light would go to infinity. They actually, all of their equations that fit that curve really nicely on the side that was visible to them completely fell apart when it came to ultraviolet. And once they were able to actually start doing ultraviolet exposures, they realized that, in fact, the intensity of the light didn't go to infinity. In fact, it abruptly went down. And it seems like a super nerdy thing to lose sleep over, but it sent the whole physics community into a complete tailspin because they couldn't understand how the classical theory could fit the curve so well, but fail so miserably to reproduce reality when it came to these high energy light sources like ultraviolet and beyond. And without boring you guys to tears about the solution set, the actual solution came down was actually what gave birth to the concept of the photon, the idea that light had to be actual discrete numbers of waves. You couldn't have half a wave of something. And without sort of killing you with math right now, the introduction of the discrete action, quantum of action, the birth of quantum physics happened when people realized that by essentially saying that light had to happen in full pulses, the curve could be adjusted in such a way that it actually fit the data perfectly ever after. And we ended up with all the black body maths that we've talked about in this course so far. So that's an interesting situation where you have a singularity appear and infinity appears in your math at some level, and it doesn't in this case, it didn't match experimentation, right? There was no way that this made any sense. You clearly weren't getting an infinity of intensity of this ultraviolet light. So people had to actually sit down and rethink the situation. But they were able to move past it eventually. That's kind of what I'm trying to get at. It's not unheard of that singularities will appear in mathematical modeling of situations. It generally comes down to ignoring a boundary condition or misinterpreting some fundamental aspect of reality. And of course, I would submit to you that that has to do with the gaseous nature of the stars themselves. Remember, liquids are essentially incompressible. Gases, especially ideal gases, are indefinitely compressible so long as the container applies it. So again, the equations that govern the behavior of stars are rooted in the ideal gas laws, which assume a gas pressure despite not having a surface, and it really gets out of control from there. So that was interesting, the ultraviolet catastrophe, this singularity. But the gaseous stars persist. The singularity, the Chandrasekhar limit persists. People love the explanation. Like I said, there are definitely places, including in our own galaxy, where bodies appear to be orbiting a spot with no light. And so this provides a nice solution. I don't know, nice is the right word. It provides a solution to the problem. And of course, the consequences are absolutely astounding. So let's see, what I wanted to say here about this. There was some...
Have you seen the clip of the simulation that NASA made last year going into a black hole?
No. I bet it's cool, yeah, and that's what I'm saying. I don't want to break any hearts here. I love the sci-fi myself, too.
A lot of like supercomputers that put it together and stuff.
I bet. We're going to talk about this image that they actually prepared of the black hole. And you want to talk about supercomputers. I think I have seen that, actually. Yeah. We'll talk about it. I'm actually going to kind of zip into that section now because I really want to have time to go through that. It's a really interesting masterclass in data processing. There's literally like tons of hard drives involved, like actual physical tons of hard drives that were stripped down. We'll talk about that in just a second. To create that image that I showed you at the beginning of class. Yeah.
Like 129,000.
I have the numbers. I'll get to it in a second. It's actually quite astounding. It's a little bit heartbreaking, though. We'll get there in a second. So, we're talking about in order to get to this point that you're shielding, that light is no longer able to even escape. You've got to compress things unbelievably. We're talking about like squishing the Earth down to the size of a penny before you're able to actually exclude light under these modelings of how this goes. All right. So, like I said last week, the difference ultimately, when you go looking for something like this, how do you look for it? Well, again, you're looking for a point that doesn't have any visible light. It turns out that neutron stars are kind of similar. The only difference seems to be the gravitational effects. The neutron stars aren't quite as big as what we would call a black hole. There are some X-ray signatures, which is really interesting too. It's kind of an interesting contradiction of sorts that one of the signatures of these places where we think that these gravitational interactions is happening is that the emission of light, particularly in the X-ray, actually occurs and points us back to these locations at the end of the day, which is strange because X-rays are, of course, a form of light. And how in the world these emissions escape while the others don't is very interesting. All right, so there's one more thing I want to talk about before we get to, before we look at that image, because that's going to kind of be the real kicker for us. And that is gravitational waves. So before we got that image of the black hole, which is quite honestly what a lot of people stand behind when they claim that these things have been observed, and we'll discuss whether that's true or not, had to do with these gravitational wave detectors. Anybody heard of gravitational waves before? Yeah, a little bit. This is kind of interesting. So a natural consequence of relativity as well is that naturally there's a flip side to the way that gravity propagates during different energetic exchanges, in that there are actually ripples of gravity that are sent out sometimes generally speaking, when huge objects merge with each other. Now, people went looking for this, and well, as often is the case when people go looking for things, they end up finding it. So they built this really interesting detector. It's actually enormous. So it's on the order of kilometers. They have these big hallways. They essentially send a laser beam through a two-way mirror, and it sort of splits the laser beam into two parts, and they go down the hallways and come back. And if the waves are in phase, then you just get a steady signal of the light back at the detector. But if one of the arms wiggles in any way, particularly in the, orthogonal directions, if it is in somehow shrinking, for lack of a better word, or extending, then those light waves are going to get out of phase because it has more distance to travel. And so this is a classic interferometer setup. And what they did with this was, all this data came out back in 2017, I want to say, was the big one. What they did was they actually started looking for events that could be recorded that would show differences in this kind of motion at two different sites. So one of them, I think, was in New Orleans. The other one was up in Washington State. And they basically went looking for events that they could correlate between these two detectors. They found one. And now, reaching back a few years before this, when people started really taking gravitational waves seriously, there was actually a Nobel Prize given because what a group of scientists did, I think it was two different scientists working together, they basically had showed that if there was a merger of enormous bodies, they used neutron stars, if I recall correctly, if these two neutron stars were to blend together, that they would emit gravitational waves. And so they didn't actually observe them when they got the Nobel Prize. Apparently they just did such a bang-up job of the mathematics that everybody bought it and said, this makes sense. So when they discovered some correlations at the actual LIGO gravitational wave detector experiment, they went to this enormous catalog of neutron stars that they'd been observing in the sky, and they tried to see if one of them, any pairs of them, would fit the data really nicely. Turns out there was one. And so everybody congratulated themselves. I actually don't know if Nobel Prizes were given, but I would not be surprised. And the merger of the neutron stars had been detected as a result of this. Now, they've since done a lot of gravitational waves in neutron stars, which is quite interesting. And you'll notice that really the difference between the spread here, so we have black holes in purple, we've got let's see here, neutron stars down here. It's really just the amount of mass that's required in order to pull these off. Some of these, these are all black holes up at the top. So really just the difference between a neutron star and a black hole just depends on how much mass is observed in these transactions. Now, the thing I kind of like about gravitational waves is that they bear a really interesting correspondence to light itself, right? So we've talked, if you guys can remember way back, we talked a little bit about, ideas for what the heck light is. It appears to be this strange kind of wave that's transverse. Transverse is kind of like the ripple at the surface of a pond. It's a back and forth motion. And you say back and forth of what? And it turns out that it's the polarity of the electric field or the magnetic field. Either way you want to look at it. The gravitational waves also are one of the only other waves in the universe, other than the surface of a pond and light, that have this transverse wave to them. So that's really interesting to me because it seems to make sense that if there is some medium responsible for, well, I cringe to even say that, there must be some sort of mediator of light and gravity, right? I doubt that the Earth is being held to the sun by magic, in other words. The details of that medium have eluded science for the past 150 years, but there must be some explanation, and I find it deeply reassuring that the wave dynamics of light, which is actually a pushing force, should be in some sense inversely related to the wave dynamics of gravity, which is a pulling force. In other words, you wouldn't need two separate media in order to pull off these two different waves. They're somehow compatible with one another. So I find that personally quite reassuring. Okay, so this is this is the black hole image that made a bunch of headlines a few years ago, and is conspicuously absent from your textbook. So, what's going on with this thing? Did they actually take a picture of a black hole? Is this the picture that they took of the black hole? And if not, what in the heck is going on? If so, then my goodness, something really amazing is going on, and we can all rest assured that light absolutely does get gobbled up by these massive objects at the center of galaxies and so forth. First thing I would point out is that the project was done using a similar interferometry process where you have radio telescopes all over the globe that are set up and staring at a single galaxy very, very far away all together. And they're staring at it, and they're able to make resolution, they're able to resolve their images based on the way that the radio waves coming from that galaxy interfere with each other. And if you guys remember all the way back to our parallax discussion, the resolution of a parallax measurement has to do with how big your baseline is. And so they set up this huge baseline that's, I think, between Chile and Spain. It's an enormous baseline for this measurement. And there's all these telescopes involved. This actually involved 200 different universities in compiling this data. 20 different countries were devoted. And the telescope was called, it's actually a lot of different telescopes, but the telescope was actually called the Event Horizon Telescope Network, which, I think that the naming of your telescope with what you intend to find with your telescope is a particularly suspicious bias that you're imposing on the project in the first place. At any rate, they published this huge paper which basically showed how they had done all of this work to trim down this image that they'd taken with these interferometry experiments and produced this image of the black hole. Now, they were very much congratulatory about this as it happened. All the science news websites were very, very excited. But within a few days, a number of groups actually started to independently analyze the data themselves. So one of the cool things that's happening today that never happened in the past is that when you do a paper, especially if this was published, I think this was published in Science Magazine, which is probably the second most prestigious journal in all of science. Maybe the first on a good day, depends who you talk to. Anyways, they published it, and in these journals, you have to actually upload your raw data. So, we were talking about doing that experiment earlier with the person walking and measuring the time and distance, and you supply the chart. Well, the papers always have the chart, the graph that illustrates what's happening and so forth. In this case, they show an image. But they also uploaded, they made accessible all of their raw data and all of the different layers at which they process the data. So within a few weeks, all of these different people started analyzing the data themselves. And what they found was a little bit disturbing, actually, as a result of it. And I think that it's illustrative, not necessarily to shame this group, but in order to talk about, what it looks like to do good science versus bad science. So the paper that I'm going to be picking on is by this group, by Miyoshi et al. This is a Japanese astrophysics group. Now, when they reanalyzed the data, these are quotes from the paper, actually. They actually found that they couldn't even resolve anything approximating a ring structure like what was seen in the photograph. And in fact, they actually ended up with something much more like a knot, like a core of brightness. And even worse, this is where things get really, really weird. They note that the signal to noise ratio in these detectors was essentially 1. Does anybody know what signal to noise is? What is it? Yeah, so if you go to like a really noisy bar and you try to whisper to somebody, the noise is going to overcome your whisper, right? So you kind of got to shout at bars because you're trying to get your signal over top of the noise. Now, in this experiment in particular, the signal to noise on some of the most important telescopes in the entire interferometry project was at best 1, which is essentially saying that you had no signal at all because it was all noise. In other words, you can't distinguish your signal from the noise. What's even worse is that the final image that they pulled up for this thing is actually taking 1 pixel per billion pixels. So they threw out 9,999,999 pixels for every one pixel that they saved for the final image. Based on what? Very difficult to say. So in reality, the final image that was constructed actually had the equivalent of, do you guys know what a voxel is? It's basically a 3D pixel. They actually had 6 voxels worth of image data from the original image collection points that went into the construction of these. So when you actually look at this galaxy, it looks like this. It looks like a big glowing ball of something. In the different photo spectrums, you can actually resolve this jet coming out of the thing as well. So they basically took this image and they processed it as hard as they possibly could, stripping away way more than 99.9% of the data that was coming into them based on what they essentially thought a black hole should look like. And then they published a paper of the image where they did a bunch of smoothing Gaussian functions. They ironed out those 6 voxels into something that looked like a ring structure and called it a black hole at the end of the day, which is really unbelievably abysmal science. So that's kind of equivalent to saying that you could go to the doctor, get an MRI, and you could reconstruct based on, let's say the MRI has a resolution of a millimeter or something like that. In other words, you can see individual veins. Anybody ever had an MRI before? Me? I've had one. It's cool. You could see individual veins on an MRI. But then they're saying, no, you can data process that image of the MRI and be able to see the individual blood vessel cells inside of the blood vessel as a result of it, which is, of course, nonsense. Nobody could actually do that in a million years. So it's an incredible hatchet job of data processing and the stripping away of data points rather arbitrarily in order to produce this image. So that's M87. That's the galaxy. It's 54 million light years away. Is there a black hole at the center of the thing? God only knows, really. But something interesting is happening at the center of these galaxies. And that's kind of where we are going to head with this next, because galaxies don't seem to be doing what they're supposed to be doing. There seems to be something absolutely incredible happening at the center of galaxies. There's an enormous output of energy in the form of these central jets that emit from them. The whole galaxy, like I said, doesn't even really seem to spin as if it's a gravitationally bound object. It appears to move as a single homogeneous unit, more or less, which is really, really bizarre, because in our solar system, the things that are closest to the sun go around the fastest. That's how gravity works, right? They're feeling the tug the hardest. The galaxy is not like that. It kind of moves all together, which is really, really bizarre. And so we're going to need something extraordinary to explain why it does that. Might be a black hole, might be something else. Now, there's a couple of other possibilities here too I might point out. So, one idea that people are legitimately entertaining that would avoid the need for singularities. By the way, before I get there, it's worth mentioning that people right now are trying really hard, especially in the particle physics, fundamental physics world. They're trying to unify the very large with the very small, which means that they need some sort of quantum theory that links with gravity. There's no quantum theory that unites gravity with what's happening at the subatomic level. And every single attempt at quantum gravity does not produce these singularities that are necessary for these black holes. So there's very much an impetus for people to solve the problem of what the heck is happening at the center of galaxies without black holes. And one of the possibilities that people have been playing with is something called supermassive star remnants, which sounds a lot like what we started out the class with talking about, which is basically things that have these cores that are left over. Of course, under the gaseous model, you're left with cores after these violent explosions. But some sort of metastable core that's left around, which is huge and cold and invisible to luminous light, in other words. There's another possibility called EMOs, this extended massive objects that people suggest. They could just be essentially really dense objects that are kind of clustered together at the center of these galaxies. Think maybe a pile of old dead stars, something like that. So there's some interesting ideas that are even coming out of the mainstream working under the gaseous model that could solve this problem without resorting to violating boundary conditions and singularities and things like that. But at the end of the day, I have a feeling that you know, we have a tendency to see things that that we want to see. You know, you guys have pointed out, I agree that the movies about black holes are fantastic. It's really fun. Perhaps you guys have had this experience before too, where you like come across something out in nature, like this stump, and you see a face on it, and you think, that's weird that the stump has a face on it. But then you think, nah, I'm just seeing faces in the stump. And why do you think that we see faces in stumps? It's like, well, because human beings are finely tuned to seeing faces and remembering faces. I don't know if you guys ever thought about it, but you can pretty much remember every face of everybody that you've ever met before. That's an extraordinary thing, considering we all basically look the same. We got 2 eyes, a nose, and a mouth, and hair on top or whatever. It's kind of amazing that we can actually distinguish faces. And so we have some structures in our minds which are set up to recognize faces. Of course, when we go out into nature and anything looks even halfway like a face, we're going to see faces everywhere. I think there might be something to that in this black hole discussion as well. And I think it might belie what's going on with that black hole image study that I showed you guys too. It's like, if you're absolutely 100% convinced that the only way a supermassive star ends its life is by collapsing on itself and forming a singularity, then you should absolutely expect that you can take a picture of one at the center of a galaxy, and you should absolutely expect that you're authorized to do whatever you need to do to that data in order to get that image, because you know that it has to be there, right? So, I would rest my case with the idea that whenever you see something like dark matter, dark energy, black holes, whenever you see this kind of dark stuff looming around in a science presentation, it generally means something that we don't know what's going on yet. And that's okay, because we've got all the time in the world to figure it out. So, from here, we will start playing with the organization of galaxies, and we will eventually move towards looking at galaxies' relationships to one another, and hopefully by the end of it, try to reach some understanding of why in the world people think that the universe was born, period, but born 13.8 billion years ago, and why they think that it's going to end in a very sad, cold heat death. And we're getting close, folks, so hang in there and check out your final projects. Tell me if you got questions, email me, turn in your missing assignments, and we will all get there very soon. Have a good week, guys.